So welcome everybody to week number 4. Today we will talk about stuff that has a lot more to do with ham radio or radio in general than what we did last week. But talking about last week, I hope I did not scare anybody away with uh, an evening that was pretty dense. I know that, but unfortunately we had to get through it. And I hope you are still working on digesting all the topics that we touched on last week. As I said, there's a reason we bring this very early in the class so that you have a long time to actually get through that chapter and make those things that we talked about stick. Having said that, do you have any questions for me about what we've done so far?
No.
Okay, good. So the usual reminder again to sign up for your FRN and the testing. We still only have 2 people signed up, so there's plenty of room, but don't forget about this. So today we'll talk about 2 things. First one is propagation. How do we get our signal from the transmitter to the receiver? And the second part will be about antennas and feed lines and stuff that have to do with antennas and actually getting our signal into the air. So propagation, what is that? It's how we get our radio waves from point A to point B. And there is not just one way to do that. Radio waves can propagate in many ways depending on the frequency of the wave and the characteristics of the environment. There are 3 basic, very basic propagation methods, which we will touch on. And then we will talk about some of the more a little bit out there ways of making communications. So the 3 basic ones are line of sight, which is exactly what it sounds like. If you can see something, you can talk to whoever is on that other spot, ground wave and sky wave. So line of sight is the most simplistic way our radio waves can travel. And in this case, they travel in a straight line from the transmitting antenna to the receiving antenna. And we call that the direct path. There's also a long path, and that goes the other way around the Earth. So I'm in Rochester. Buffalo is about an hour down the thruway. If I drive that 1 hour to Buffalo, I'm taking the direct path. If I'm driving the other way, get to the ocean, start to paddle, and then come all the way around, we call that the long path. And in order to get to Buffalo, I would not do that. But our radio waves sometimes do this for us, and the long path might actually be easier to talk to somebody versus the short or the direct path. But for line of sight, we are limited to this direct path. There is no long path for line of sight. There is always some attenuation of a signal as our radio waves travel because they will spread out. So our signal gets weaker and weaker and weaker as it spreads out. This line of sight is the primary way of propagation for VHF and UHF signals. By now, you have a rough idea about VHF and UHF means. Does anybody know the 2 frequency ranges that are associated with VHF and UHF?
Without looking at your notes.
Yes. VHF is 30 to 300 megahertz, and UHF is 300 megahertz. Oops. Hit the wrong button. To 3 gigahertz. You need to get familiar with these ranges because there are questions where you need them. So again, in the VHF to UHF, so that is 30 megahertz all the way up to 3 gigahertz. This is the primary way of propagation. When we talk about ground wave, lower HF frequencies. So now we, again, just to remind you, HF is 3 megahertz to 30 megahertz. And here we talk about the lower HF frequencies. This may actually be a little bit lower than what we have here. So it may also be in the 1.8 megahertz band or the 160 meter band where we have this. Our radio waves can actually follow the curvature of the Earth. They kind of hug the Earth as they propagate. And these waves will travel beyond the range of line of sight. So with this, we can reach a few hundred miles on those bands that we use in amateur radio. I can definitely not see a few hundred miles. When I'm standing on the ground, I can see about 7 miles out. And that already takes the curvature of the Earth into consideration. So I'm here. And then I look this way, and if I look just above the horizon, I can see somebody who's standing, who's the same height as me, about 7 miles away. So we see about 3.5 miles to the horizon. And if I'm looking at somebody who is the same height as me, we get about twice that distance, about 7 miles. And if we both have our handheld radios, we can talk to each other. More than that, if I'm standing on the ground, will not work. So if you see radios that advertise 50 miles or more range in VHF and UHF frequencies, don't buy them. They are lying to you. It doesn't matter how much you pay for your radio or how much power you run. This is a physical limit and we cannot get around that. Now, if I'm on a mountain, that all of a sudden changes things quite a bit. There could be 100 miles between these two mountains, and I can actually see the other mountain summit. So line of sight means if I can see it, I can talk to it. And this is why we put the repeaters that we use up on tall buildings, mountains, tall masts, and so on. So ground wave hugs the Earth and can travel beyond the line of sight. Now, before we talk about skywave, we have to talk about how radio waves can change directions. And first one is our waves can be reflected by a conductive surface. Keep in mind, light, visible light, is also an electromagnetic wave. And we know from mirrors can reflect light. With the radio waves that we are dealing with, a regular mirror will not do. We actually need something that is conductive. Our ground is actually conductive, not very well, but it does conduct. Water, especially seawater, salt water, is very conductive. Buildings, if they are made out of metal, then usually they are conductive as well. And all these things can reflect our radio waves. And we can take advantage of that. Now, reflection means a straight line in. Oops. So let's say we have our reflective wall here, straight line in, straight line out. It gets reflected. Refraction, on the other hand, is kind of like reflection, but there is some bending involved, and it doesn't go in straight lines. This bending occurs when waves encounter a medium that has a different speed of light. What the heck is he talking about? Didn't we just learn that speed of light is 300,000 kilometers per second? Only in vacuum. When we look at the speed of light in other mediums like water or air, then it's actually a little bit lower than that, or a lot lower than that in some instances. When we look at electric field lines, this may only be 2/3 of the speed of light that we have in vacuum that we have on a feed line. So refraction, or this bending, occurs when our waves encounter a medium that has a different speed of light, and how much it gets refracted or bent depends on that difference. And the same thing actually happens with light as well. And we see that as, for example, the mirror surface of water when we have a pond and we see like the very mirror-like surface of the water. This is an effect of having a different speed of light in water. But you don't need to know about that, but you need to know about refraction. There is one other thing that can happen, and that is diffraction. So we have the reflections, we have the refraction, and now we talk about diffraction. Diffraction occurs when a wave encounters a sharp edge. And sometimes we call this knife edge propagation because of this sharp edge, or a corner, which kind of looks sharp as well. Especially when you run into it and you end up with a big bruise, you know that was quite a sharp corner. So when we look at our little diagram here, we have our signal source here, and here we have this knife edge. This could be the top of a tall building. It could be the a mountain range, the top of a mountain, and our signal is going out in all directions. And then when it hits this knife edge, it gets diffracted and it gets like split up. And we have these areas where we have our signal. And then we have these zones here that are white, which we call the shadow zones, where we don't have a signal. But as you see, my signal travels in a straight line here to this knife edge, and then it could potentially go down. So it changes directions, and that would be a way to get your signal into a mountain valley that is here. So if you aim your signal, if you aim your antenna at that top of the mountain, some of your signal may actually go down into the valley, and you can talk with somebody who's behind that mountain, even though that mountain would otherwise block your signal. And again, this is something that happens mostly in the VHF and UHF segments. Now, when we actually look how far out we can talk to somebody, line of sight for radio waves is actually a little bit better than what we can see with our eyes. So the range that we get is slightly better than the visual line of sight due to a gradual refraction, which we just talked about, this bending of the radio waves. So we have a visual horizon. This is how far we can see. And then we have this radio horizon, which goes a little bit beyond what we can see. And there is a question about that. UHF signals penetrate buildings better than HF and VHF signals because they have a shorter wavelength. Higher frequency means shorter wavelength. And to give you an example, VHF would be, for example, 2 meters. The 2-meter band is in the VHF segment. And VHF would be, for example, 70 centimeters. This is about 6 feet, a little bit more than 6 feet, and this is about 2 feet. A little bit more than 2 feet, but gives you a rough idea. Buildings may block your line of sight, but reflected and diffracted waves can get around these obstructions. So sometimes when you aim your antenna straight at a building, your signal gets blocked. When you aim it at the edge of that building, your signal may get around that building and will actually propagate behind that building.
Hey, Carl,
Yes?
I was over at the Federal Building with Mark Peterson, and he
Yes.
had his handheld radio, and he was able to contact the Bristol Mountain repeater from the parking lot at the Federal Building.
Yeah, and there's a pretty good chance that the building was right in the way, and he
It
would
was.
not have been able to see it, the repeater. But that signal went up to the top of the building, and then a part of the energy got redirected and went straight to the repeater.
Yeah, because you couldn't see out of the parking lot at all.
Yeah. So we can take advantage of that. Even though you think you cannot reach anybody because you're in the middle of Manhattan and there are buildings all around you, your signal might actually get out. It might not get where you want it to go, but it will go somewhere. Okay, so speaking of all these different ways that our waves can travel, and again, we are still talking about VHF and UHF here. So we have direct line of sight, we have diffraction, we have reflection, we have refraction, which means that there's a good chance that when I send a signal from here to somebody a couple miles down the road, my signals will travel on different paths and therefore will arrive at different times. Now, of course, speed of light is pretty fast, but there might be small differences in when those signals arrive. And this is what we call multipath, and results from reflected signals arriving at the receiver by different paths, and then they will interfere with each other. And one type of this interference is called picket fencing. And this is the rapid fluttering sound that we get from this multipath when we have a moving transmitter. So a car is moving, somebody is talking in that car to us. And because those waves arrive at different times at our receiver, we end up with interference that at some point in time will eliminate that signal completely, and at other times will actually enhance that signal. So we end up with the signal dropping in and out and in and out and in and out rapidly, and we call that picket fencing. When you drive around with your car radio on and you stop at a red light, you may have noticed sometimes you stop and the radio signal drops out. And then you move your car by a couple of feet, and then you have your signal back. This is one effect of this multipath propagation, and sometimes moving just a few feet will actually be the solution to the problem, and you can get your signal back. So both of these are answers to questions on the test. And now we will leave the Earth behind and go into space. So what we've talked about so far was earthbound, line of sight. I'm standing on with my 2 feet on the ground and I'm talking to somebody else somewhere in a similar situation. And our waves, even if they go up here, they don't do anything. They'll just go out into space. When we look at what's above us, it actually gets pretty interesting because there are a number of different layers up there that will do things with our radio waves, with some of our radio waves. Down here, you see we have the Earth's surface, then we have the clouds. And where the clouds are, we call this area the troposphere. And we'll hear about that in a little bit. But if we go further up, we end up with layers that are named by letters. We have the D layer, the E layer, and the F, actually the F1 and the F2 layer, which combine into the F layer at night. These layers up here will do things with our HF signals. But let's start at the Earth and let's move up slowly. So the first thing that we get to is the troposphere. The troposphere allows for tropospheric propagation or tropospheric ducting, like the ductwork that you have in your house for your air condition. Tropospheric ducting works like a duct. It sucks in your radio wave and helps it to get a few hundred miles out, and then it comes out and goes back to Earth. And this all happens in the same areas where we have clouds, where our weather happens. So this is up to about 30 miles high. Radio waves can be reflected or scattered by clouds, rain, and density variations in the troposphere, ranging up to a reach to about 300 miles. So even though I'm standing on the ground with my handheld radio and I, in normal circumstances, cannot talk to anybody without the help of a repeater who is more than 7 miles away, all of a sudden the switch gets turned on and I'm talking to somebody in New York City via this tropospheric ducting. And what happens is we have temperature inversions. So usually the higher up you go, the colder it gets. So we have 70 degrees down here, then we have 40 up here, we go even further up, then all of a sudden it gets really cold. Sometimes things change and we get to a point where we have like 40 and then all of a sudden it goes back up to 60. Now I'm just making up these numbers. Don't hold me to it. The idea here is we have, as we go further up, it gets warmer. We have temperature inversion. That's the important thing. And that creates denser area that will then use diffraction to bend these waves and like funnel them through the air to some spot a few hundred miles down the road where we then let them out again and they will hit a receiver. So this is tropospheric ducting because we use these ducts in the troposphere. When we go further up, so we said up to about 30 miles was the troposphere, then we go up to about 260 miles. Here, the air gets really thin. And what can happen is that ultraviolet light, the type of light that makes our skin burn and causes skin cancer if we are exposed to it too much, this high energy light can actually knock electrons away from atoms in the atmosphere. And by doing that, it is creating a medium that's electrically charged. And because the atmosphere is so thin, these free electrons take a long time to recombine with an atom that is missing an electron. And if the air is much denser, like down here, this will happen instantaneously. But up there, it takes a while, and this creates this electrically charged area in our atmosphere. And I said reflection for radio waves happens on electrically charged or electrically conducting surfaces, which this is. So our signal goes up here and then gets bounced back. And this is how we can actually get our signals around the Earth. Now, problem here is this only happens with HF frequencies, usually. There are some exceptions, but usually it's limited to HF. So we have this ionization, this making of an electrically charged environment in the atmosphere. And this can refract or bend our radio waves. And this usually happens up here and sometimes here. Not here. The D layer actually gets always in the way. The D layer is where our radio waves go to die. They get sucked up by the D layer, and they, if things are bad, they will never leave the D layer. They will never come back out again. But when the D layer is not that active, they go straight through them and get reflected, or actually refracted, because there is a slight bend up there. It's not a nice angle. But for the purpose of discussion, we can just call this reflection and be fine. So this is how HF radio is a lot of fun, because it allows me to talk to somebody in Australia on the other side of the earth. And I actually, just 2 days ago, I talked to somebody in New Zealand. Not quite all the way to Australia, but close enough. It doesn't happen all the time. You need to hit the right conditions, but then it can work. One thing that potentially interferes with what we do here or enhances what happens in the ionosphere is the sunspot cycle. The level of ionization that we have depends on the intensity of the radiation from the sun, this UV light, and potentially other stuff that the sun sends out. The radiation from the sun varies with the number of sunspots on the sun's surface. Now, this does not have, the sunspots are not causing this. The sunspots are also a side effect of something that's going on inside the sun. So one side effect is there are sunspots, a lot of them. Another side effect is it charges up our ionosphere. A higher number of sunspots results in higher levels of ionizing radiation emitted from the sun. And the sunspot activity follows an 11-year cycle, roughly. So again, the sunspots don't cause this radiation. They're just another side effect of some processes inside the sun. Here is a chart that plots the number of sunspots over a number of different of these sunspot cycles. So we see we're going back to the early 1900s. And when you look at these peaks, they are at different levels. Some of them are really high. And then others are not quite as tall. This is where we currently are. And the red curve here is the forecast of what our sunspot cycle number 25 might look like. And when you compare where we actually are to what the forecast is, we are actually already higher than the forecast. And we might still be a year out from the peak. This is not exact science. This is a little bit like forecasting the weather. Sometimes the weatherman hits it spot on. Other times it's way off, and we are shoveling 3 feet of no participation in the forecast of our driveways. Same thing happens here. It's not an exact science. We don't really know when the peak will be. It's possible that where we are right now is actually the peak, and we will actually die down earlier than the forecast, or it could keep on going and sustain itself for a little bit longer. We do not know. What we do know is we're not hitting this. Everything so far is not looking promising to hit this. When we look at the last cycle, it had two peaks. We might see something like that. So again, nobody really knows. I have the link to where you can find this on this slide. And this is actually a pretty interesting topic. And if you are interested in making contacts on HF, then you need to keep an eye out on the space weather forecast bit. But this is a little bit down the road for you. So the ionosphere can refract or bend radio waves back to Earth, acts like reflection, and most of this occurs in the F layer, F1 or F2. How much reflection we get depends on the frequency and the angle of incidence. So if my signal goes straight up, it may never come back because I need a certain angle. You see here, this is too low and it gets warped. If that angle is right, then we get this refraction, and then a different angle or a different frequency, the frequency might be too high and it goes straight into space, which is a frequency that we actually would use to communicate with spacecraft. So if we have some satellites up there, we don't want our signals to be reflected back to Earth. We want that signal to go actually to that satellite so that we can control it. So by picking the right frequency, picking the right angle of incidence, we have control, some control over where our waves will go. So we call this the sky wave propagation, or sometimes skip propagation, because that wave skips off the ionosphere. And this is responsible for most over the horizon, further than the horizon, propagation on HF and low VHF bands. So 10 meters would be an HF, 6 meters would be low VHF. During peaks of the sunspot cycle, you're joining ham radio at the right moment because we are just approaching that peak. So you can actually take advantage of that. If you join at the bottom of the sunspot cycle, it can be pretty boring. The skip is very rare on 144 megahertz or 2-meter bands and higher UHF bands. Doesn't mean it does not occur. It's not something that happens on a regular basis. Each ground to sky to ground trip is called a hop. And sometimes our signals have multi-hop propagation. So it goes up and down and up and down and up and down. And sometimes that signal actually comes all the way back to you, which is the long path. And you can actually hear the tail end of what you just said into the microphone in your headphones when you let go of that PTT, that push to talk button. So you can actually hear yourself. It's not a long segment. It's I think a third of a second or so, but sometimes you can hear yourself. Now, just like with VHF and UHF, our signals can take many different paths through the ionosphere. And we have that multi-path problem again. So randomly combining signals that travel different paths at the receiving antenna can get partially or even completely canceled. And they can create this irregular fading as the ionosphere changes. So this is not a static thing up there, it moves. And that can mean that your signal fades in and out and in and out. This results in echo and flutter distorted speech, and also affects Morse code. So in this case, our brains are there to fill in the blanks. If like a syllable is missing, you can fill in. If two words are missing and they're the right words, your brain can fill in those blanks and you know exactly what the other person said. If we do this with data signals, then this fading will cause data errors for digital signals. This is the answer to one of the questions. So we've done the F layers. Now we go down to the E layer. Here we are dealing with something that's called sporadic E. Sporadic means it doesn't happen all the time. It happens sometimes. So sometimes we have highly ionized patches in this E layer that can reflect HF and VHF signals. And this works best on 10 meters, 6 meters, and 2 meters. So this is not for the lower HF bands or for the UHF bands. Another way we can end up with something that's highly ionized is if we are dealing with the northern lights, the aurora borealis. The aurora near the north and south poles can also reflect VHF and UHF waves with a very distinctive, distorted sound. This is the answer to one of the questions. And I will have a recording for you in just a minute that might illustrate what that sounds like. And once you've heard this, you will never get this question wrong.
What was that again, Carl? What was the slide before that?
This here. You are looking for the very distinctive distorted sound for aurora propagation. So you have the northern lights, you aim your antenna at the northern lights if you can see them, and that then reflects those signals back. And again, we are talking about VHF and UHF here, where you usually have line of sight. And usually, and all of a sudden with the aurora, your signal travels a few hundred miles. So the ionosphere is really interesting. And as I said, if you are into HF and you want to talk to somebody around the world, then this space weather dashboard here is a good resource. And you find things like what we have here. Let me turn this up. So little movies that illustrate what's going on. This movie shows D-layer absorption. So the brighter or the redder the spot is, the more your signals get absorbed. And sometimes it gets really bad, like what we see here. We have this explosion. Something is coming in from the sun and it's just lighting up our diagram here. And the more red it gets, the fewer signals it will let pass through the D layer. So when you see this lit up, you know your signals are not making it anywhere, and you can just do a crossword puzzle or something else and skip the playing with the radio. So you will find things like that on the space weather dashboard. This link gets you to a YouTube recording of aurora contacts, and keep your fingers crossed. Sometimes that sound does not travel through Zoom. We'll give it a try.
5 and 8, Aurora. 5 and 8, Aurora. Fox, November 3.
Can you hear that? So you heard how distorted it was. This is a typical sound of an aurora contact. So once you hear that sound, you will get that question about what an aurora contact sounds like correct, hopefully.
5 and 8.
So again, a key to getting our signals out further is to have something that is electrically conducting, or as we've now heard, highly ionized. Our ionosphere, if the sun is doing the right thing, can be ionized and help our signals. Aurora can do that. Another thing that can do that is if a meteor is entering the Earth's atmosphere and is burning up, it leaves a trail of highly ionized gas behind. That trail lasts for a few seconds, and we can use that to bounce signals off these meteor trails. And we call that meteor scatter. And this is usually done best on the 6-meter band. This is an answer to one of the questions. So this happens mostly in the E layer. Meteor scatter and sporadic E supports contacts up to about 1,500 miles. So this is quite a bit different than the 7 miles we get standing on the ground with our HTs. And this again is all VHF and UHF. So any questions about propagation? Then let's see how much of that stuck. I won't go through all the questions. I will skip some. You need to just practice them on your own, but with what you've heard so far, you shouldn't have a lot of problems with that. So why do VHF signals strength sometimes vary greatly with when the antenna is moved only a few feet?
Let's see.
It's C, it's that multi-path where we can end up with our signals traveling different paths, arriving with a slight delay, and then either canceling each other out or reinforcing and amplifying that signal. What is the effect of vegetation on UHF and microwave signals? We haven't talked about that, but you should have seen this in your book.
Absorption?
It's absorption. And you know what it is in vegetation that will make the signals get weaker?
Guessing the chlorophyll?
It's the water.
Oh, water. Yeah.
And we'll see that a couple more times. And this applies to UHF and higher signals. They do not like water. If you have a satellite dish and we have a strong rainstorm or a snowstorm, you know what happens to your signal? It gets absorbed in that moisture and you can't receive anything anymore if it gets really bad. Same effect.
That makes sense when your satellite dish goes out during a snowstorm or a rainstorm.
Yep. Because they are using microwave signals. So not any different than what we would see with our ham radios. What's the meaning of the term picket fencing?
B.
It's B. It's a rapid flutter on mobile signals due to multi-path propagation. What weather condition might decrease range at microwave frequencies?
C?
Yep. So again, it's water in the air. What is a likely cause of irregular fading of signals propagated by the ionosphere?
E.
D, the random combining of signals arriving via different paths. So again, same problem here. Signals go different paths and they will potentially cancel each other out. What effect does multipath propagation have on data transmissions?
B.
It's the error rates are likely to increase, because if there's something missing, the computer cannot fill in the blanks like our brains can. So there are ways around that, but that's for a different class. What is the effect of fog and rain on signals on the 10-meter and 6-meter band? This is important.
D.
It is actually B. So water is bad for UHF and microwave and up. Here we're talking HF and low VHF. And water does not affect these frequencies. So there is little effect when we have fog and rain when we are on HF. Which of the following effects may allow radio signals to travel beyond obstructions between the transmitting and receiving stations?
A.
It is A, yes. What type of propagation is responsible for allowing over-the-horizon VHF and UHF communications to ranges of approximately 300 miles on a regular basis?
A.
It is A, the tropospheric ducting. What causes tropospheric ducting?
Temperature inversions.
Yes. Why is the radio horizon for VHF and UHF signals more distant than the visual horizon?
C.
Yes, the atmosphere refracts radio waves slightly. So let's skip over these. What is the characteristic of VHF signals received via auroral backscatter? You've heard it.
Distortion.
Yes. In addition, you have signal strengths that go up and down like crazy, because the aurora, when you see it, it moves. And because of that, we have multipath, and that will change the signal strength quite a bit. So the distortion is the easy part to remember. What band is best suited for communicating via meteor scatter?
6 meters.
It's 6 meters, yes. So this is unfortunately one of those questions where you just have to remember the answer, because if you don't have any hands-on experience, it's really hard to say, yeah, I've done this so many times. I'll just switch to 6 meters and then it works. So you need to remember that. But again, if you've seen this question 10 times and you got it wrong half of that times, there's a pretty good chance you will recognize the correct answer. And unfortunately, we have a number of these types of questions where you just have to remember a number. What is generally the best time for long distance 10-meter band propagation via the F layer? So we haven't talked about all the differences between the different bands and how they behave. I can tell you the 10-meter band requires a lot of sunspots. So right now, 10 meters would be a good band to be on. In 5.5 years, not so much.
So it would be either A or B.
Yes, so we need the high sunspot activity. And the other thing you need to know is that 10 meters is basically a daylight band. So it's from dawn to shortly after sunset. And this is something, again, that comes with experience. Once you've been on HF and you've seen, okay, it's nighttime, I turn the radio on, I hear, I'm on 40 meters, and I hear stations from all over the world. You know, in this case, 40 meters is a long distance nighttime band, and during the day, it's a few hundred miles. Once you get that experience, it's really easy to pick the right band for whatever you want to do. Until you get there, it's a little bit harder. And unfortunately, you need to remember questions like that.
How does it, if it travels, if you can travel like 1,200 miles on the 10-meter band in the F layer, how do you, doesn't have to be sunlight to where you're trying to receive
Yes,
and transmit to?
yes. And that gets tricky. Now, when the atmosphere or the ionosphere is charged up, it will remain charged for some time after the sun sets. So it's not like a switch. The sun goes down, it's dead. It stays active for a while. And then one thing you need to consider then is the gray line. When you look at how the whole world is lit up by the sun, there is this border between the daylight and the nighttime that we call the gray line. And when you pick the right time, you can actually use this gray line to bend your signals along that curve and make them go places that they otherwise would not.
Yeah, cool.
So a lot of us hams actually have these maps that change over time and show where the nighttime and the daylight parts are, because it helps us to make these gray line connections. Which of the following bands provide long-distance communications via the ionosphere's F region during the peak of the sunspot cycle? So we just talked about 10 meters being a band that requires a lot of sunspots. With that information, what do you think the right answer is?
Hope it's A.
It's A. It's 6 or 10 meters. And 6 meters oftentimes is called the magic band, because when 6 meters is active, magic happens. And this is the end of our first module. Any questions about propagation? So, not hearing anything. So let's start with our second module. Oops. We will talk about antenna fundamentals and feed lines and SWR, standing wave ratio. What the heck is that? You will find out about it. So when we talk about antennas, there's actually a little bit more involved than the actual physical antenna. The antenna system is the antenna which transforms our electric current into radio waves, and on the receiving side, the other way around. But we usually also consider our feed lines as part of the antenna system, and the feed line connects your radio to the antenna. And then there might be some testing and matching equipment that's involved to monitor what's going on and potentially optimize how power moves from your radio to the antenna. Antennas are pretty straightforward and a lot of fun to build, because all you need is a little bit of mechanical abilities. You don't need to be able to do all that electronic stuff that we talked about last week. This is a good project for somebody who just goes to the antenna supply aisle at Home Depot. They don't really have a thing like that, but you can buy a lot of stuff that you can use to build antennas there, like wire. So when we talk about antennas, we need to get some of these terms straight that everybody uses. So the basic thing in an antenna is the element, and that is a conducting part or several parts of an antenna design that either radiates, transmits, or receives radio waves. So when we look at what we have here, we have an element here, we have an element here, we have an element here, and here, and here. So we have 1, 2, 3, 4, 5 elements in this antenna. And those of us a little bit older will recognize this as what we used to use to receive TV signals over the air. When we look at more closely at the elements, we have something called a driven element. And the driven element is actually this one. You see there is the coax wire attached to it. So we have one driven element, and then we have what we call parasitic elements. These are the elements that are not connected directly to the feed line. So this one, this one, this one, and this one. When you look at this antenna, you might notice that this element back here is a little bit longer than our driven element. And the elements here in the front of the driven element are a little bit shorter. And we call the one in the back the reflector, and we call the ones in the front the directors. So they direct our signal towards something, and the reflector reflects the signal, which makes this antenna a directional antenna. And any antenna with more than just one element, we call an array of elements. An antenna can be resonant. We talked about resonance last week when we talked about impedance and reactance. And we said whenever the impedance is just resistive and does not have any capacitive or inductive components, we call something in resonance. And the same thing applies here. An antenna is resonant when its feed point impedance has zero reactance, so only resistance. The feed point is pretty obvious where the transmitted energy enters the antenna, where you connect your cable. We talked about radiation here. We are radiating a signal. This is not radioactivity. This is important. This is not dangerous. We are not ending up with radioactivity poisoning here. Our radiation is only emitting, our antenna is only emitting electromagnetic waves. They can still harm you, but in different ways than radioactivity. And this is actually the answer to one of the questions. So just to recap, we are dealing with electromagnetic waves, two components. We have an electric field and a magnetic field at right angles to each other. So one goes up, down, the other one goes left and right. And both of them are oscillating at the wave's frequency. They do spread out into space from the antenna. They are created by an AC current in our feed line and our antenna. And the wave and the current also have the same frequency. So whatever we stuff into our feed line frequency-wise comes out as an electromagnetic field out of the antenna. Where it gets a little bit tricky is, I said we have one wave, like the electric wave one way and the magnetic wave the other way. So E this way, M this way, but we could also have M this way and E this way. And these two different things describe the different polarization of our waves. The orientation of the wave's electric field component with respect to the surface of the Earth is what we use to define whether we are dealing with vertical or horizontal polarization. So here, my E field is parallel to the horizon, So we call this horizontal polarization. And here the E field is perpendicular to the horizon, so we call this vertical polarization. There is a circular polarization if the orientation twists as the wave spreads through space. This gets a little bit more complicated, but what we might see more often is a combination of polarizations that we call elliptical polarization. And this happens when our wave gets refracted or reflected by the ionosphere. So what comes down has a different polarization than what comes up. And this becomes important in just a minute. So why are we dealing with this? Oh, we'll get to this in a few minutes. There's one other thing we need to discuss first. So this is me. You see my radio here, you see the finger legs here, and you see an antenna here. And when we zoom in on this antenna, we see this thing here, and you can't really see it, but this is a coil. So my feed line is connected to the bottom of this coil, and then the actual antenna is connected to the top of the coil. Why are we doing that? The thing you saw is a loading coil. Inserting an inductor, this coil, into the radiating portion of the antenna, we're using this to make it electrically longer. So with a vertical antenna like this, usually you want this to be one quarter of your wavelength. And we said we use the Greek letter lambda for the wavelength. So let's say my frequency that I'm using is in the 40-meter bands. My wavelength is about 40 meters. A quarter of this would be 10 meters or 30 feet. This antenna is 17 feet tall, so it would not be a quarter wavelength on 40 meters. But if I want to use it on 40 meters, I'm adding this coil here to make the antenna look electrically longer to a signal that's traveling on the feed line to the antenna. So I can get away with a shorter antenna and still get almost the same effect that I would have had with a longer antenna. So the loading coil makes the antenna look longer to the signal that we feed into the antenna. So back to our polarization. Oh, the other thing I wanted to mention here is, this is a vertical antenna. What do you think the polarization of the signal is that comes out of this vertical antenna? Is it horizontally polarized or vertically polarized? The signal is vertically polarized. So I have a vertical antenna and it creates a vertically polarized electromagnetic wave. So why is this important? Because if we have cross polarization, bad things happen. Have you ever worn polarizing sunglasses? Do you know what happens with polarizing sunglasses?
You can't read computer screens.
Yes. Okay, good. The other thing is you can actually look through the surface of the water and don't see the reflection, can see the fish underneath it. So why can you not read computer screens? This is an effect of cross polarization. When you look at an LCD screen, there's a polarizing filter on the screen. And this is required to make whatever light comes out of your LCD screen behave correctly. Your sunglasses happen to have a different type of polarization. So you have vertically polarized light and horizontally polarized sunglasses, or the other way around. And that completely blocks the light And the same thing happens when we have cross-polarization with our antennas. So the antenna and wave polarization must match between receiver and transmitter for maximum reception. So if I have an HT with a vertical antenna on top, it creates a vertically polarized signal. And if you have another HT 2 miles down the road, and you also hold it like I'm holding it with the antenna vertical, we can hear each other. And then you say, okay, I'm tired. Let me take a nap. You lay down and you take the HT with you, and now you have the antenna going horizontally. There's a good chance my signal will be a lot weaker than it was when your antenna was also vertically. So when we have a cross polarization effect going on, the antenna elements and the wave's electric field are at right angles to each other. And that can reduce the reception, the signal strength by a factor of 100 or more. And this is why when we do VHF, UHF line of sight communication, we need to make sure that our antennas are polarized the same way. For elliptically polarized waves, such as HF sky waves, after the wave gets bounced back to Earth, any antenna will respond at least partially. And because the elliptically polarization changes constantly, it really does not matter whether you have a horizontal or a vertically polarized receiving antenna, you will receive that signal. But for line of sight, it's really important to avoid this cross polarization. It's a bad thing. And now we're coming to a fun part. We are talking about decibels. And when you quickly look down that page, you see some logarithms. And if you're like me, you don't like these. So let's just not talk about them. If you want to understand decibels from a mathematical point of view, yes, you need to learn about this. But for this class, and actually, there's a pretty good chance for the rest of your ham radio career, you may not need the math here. There are only two numbers that you need to remember. So this decibel thing is actually a useful thing because it allows us to express large, very large numbers or very small numbers in a much easier way. And how this gets expressed, more about that on the next slide. For now, there is one thing that's important here. Positive values in dBs indicate ratios that are larger than 1, and we call this amplification. So we put something into some black box and a bigger signal comes out the other end. We have a dB value for that black box that is larger than 1. We have another black box, we put something into the input and a smaller signal comes out the other end. Then we end up with a dB value that is smaller than 1. So these are the two important concepts here. dB values that are positive, +5, tell us that the signal is getting bigger. For whatever reason, we don't care about what the reason is for the dB discussion here. If that number is negative, -5, that signal gets weaker. And why are we bringing this up now? Because antenna gain is discussed in terms of dB. So we need to have a basic understanding of these dBs or decibels in order to talk about antennas. There are only two numbers that are important for you for the test and potentially for the rest of your ham radio career. So we talked about plus and minus. That is one of the important concepts. The other one is 3 dB is a number that you need to remember because that means doubling the power. I have my black box. I put 10 watts in, 20 watts come out the other side. I have a gain of 3 dB. I put 100 watts in, 200 watts come out the other side. I have a gain of 3 dB. It doesn't have anything to do with the absolute values that I'm dealing with. It's the factor between output and input that's important. So doubling something means plus 3 dB. It goes also the other way. If we put something into a box that cuts the power into half, putting 10 watts in, out come 5 watts, that is minus 3 dB. So plus minus indicates, is it getting bigger or is it getting smaller? And the 3 means it's either half or double. Does that make sense? So this is the first number we need to remember, 3, either plus or minus 3. Then the second one is 10 dB, and that is used for a 10-fold increase in power. I put 1 watt in, I get 100 watts out, a gain of 10 dB. I have some attenuator, I put 100 watts in, out comes 1 watt. Why that might make some sense in some applications, not part of this class. I have an attenuation of minus 10 dB. So times 10 or divided by 10 is 10 dB. These are the two numbers we need to remember, 3 and 10. Now, what's really nice about the dB values, that is we can add up the dB values when we're combining multiple stages. So let's say I have a box that does a times 10 amplification. Then I add a box that does another 10 time. And then I add a box that does a times 2. Now, if I want to do the math here, I say this is times 10, and then we add times 10, so that is 10 times 10, that's 100, and then times 2, so that has a gain of times 200. I have to multiply. And with nice numbers like that, it's pretty easy, but this is, if this is 7.5 and this is 19.3, it gets complicated.
What is this? What's the benefit for this, Carl? For this,
just wait 1 second, actually 10 seconds, and I will tell you. So multiplication is hard. I think we can all agree on that. Let's do this with dB. This is plus 10 dB. Oops. This is plus 10 dB. And we said this is plus 3 dB. To calculate the complete gain, I say 10 plus 10 is 20 plus 3. So this gives me a gain of plus 23 dB. I only have to add the dB values. I do not have to multiply. So this is one of the benefits of using dBs. It makes the math a lot easier.
That times 2 is because it's less than 5, correct?
The times 2 is because we're doubling.
But you have it down for 3 dB.
Yes, because 3 dB is doubling the power, or minus 3 dB cutting the power in half. And these are just some random values that I plugged in here. As I said, if we do this with not as nice a number that we have here, it gets really complicated with multiplication. With the dBs, I'm just adding them up, and adding things up is a lot easier than multiplying them. So again, the benefit of the dBs is we can express bigger numbers, bigger ratios with smaller numbers in most cases. This is an exception because my 3 dB is actually bigger than the times 2, but usually the dB number is much smaller than what we are actually dealing with factor-wise. And the other advantage is I can add them up. And the real beauty is once we deal with antenna systems, we can just say, okay, I have a loss of 2.3 dB on my feed line because that gets converted to heat. I have an antenna gain of 7 dB. In order to figure out how strong my effective radiated power is, I do the minus 2.3 plus 7, I come up with a number, and that is the combined gain of my system. So again, it makes the math easier. But for the test, there are only, I think, 3 questions on the test where you need to do dB manipulation, and you will learn the answers to these questions in no times. So, but the key is we can solve all 3 of these with just these 2 numbers, and we'll go over them when we talk about the questions. So I already used the term gain. That's the apparent increase in power in a particular direction by focusing radiation in that direction. So what does this mean? You know what this is? It's a flashlight. And when you use a flashlight, you probably know most flashlights allow you to focus that beam on a small portion, or you can spread the beam out and you can light a lot of the room without changing how much power is actually coming out of your flashlight. We do the same thing with antennas. I have an antenna that radiates in all directions. That energy gets spread out over a large area. Whereas when I have an antenna like this, it directs most of the energy into just one direction, which means I have a lot more power going into this one direction. Just with my flashlight, if I focus that beam goes quite a lot longer than if I spread it out. But there are cases for both of these scenarios. Sometimes I want the beam to be spread out because I want to look around me and see what's going on around me. Other times I want to see what's in the distance. Same thing with antennas. Sometimes I want to talk to whoever is around me, and sometimes I want to talk to the guy in Australia, and then I want to bundle that beam into just one direction and focus it. We have something that's called an isotropic radiator. Don't try to buy that. You cannot. It's something that physicists invented. And this is an antenna that radiates equally well in all directions, left, right, forward, backward, up, down. And you cannot build something like that because your feed line will always mess with your antenna pattern and will modify how well signals get radiated in the different directions. Now, what you can buy is an omnidirectional antenna, and that does not have any preferred horizontal directions. It doesn't talk about up and down. It just talks about left, right, forward, backward, and all the other directions of the compass. So our signal equally well travels all around us. And the opposite of that is a directional antenna, and that is the antenna that focuses the radiation in specific directions. Not necessarily just one direction, could be multiples, but it could be just one. And when we talk about antennas, it's always easier to look at antenna radiation patterns than to theoretically talk about how they behave. So these patterns are a way to visualize the antenna performance in the different directions. So we have our antenna here in the middle, and then different directions around it. And we say one of these we call the 0 direction. And then we measure degrees around that 0. We go to 180, which is the opposite end of where 0 was. We go to 270, and then we come back to 0. In addition to that, we have lines here, we have circles here, and these circles are labeled with dB numbers. And this is why we just talked about dBs, because they are important for antennas. The line that is the furthest away from the center of the graph, so the center of the graph is here. The line that's furthest away is this one. And I'm not going all the way around. That's usually the line that indicates the direction of, or the strongest signal that the antenna can produce. And we call that the 0 dB mark. So 0 dB means there is no gain and no loss. This is the strongest that the signal can be. And this does not have anything to do with how much power I'm putting into this antenna. Regardless of the amount of power, this thing will always be the strongest signal. Now, if I only put 5 watts in versus 100 watts, the strongest signal, of course, will be a lot less, but it will always be in this point or in this spot. So by using these dBs as relative power levels, we are not tied to any specific power that goes into the antenna. So we just say where we have 0, that is no gain and no loss. And as we get closer to the center, the weaker the signal gets. So where we have -10, we have a ratio of -10 dB. What does -10 dB mean? How much power do we get here? -10 dB is the same as 1/10 of the power. So again, we don't know how much power we put in, but we know at this point here, the power level that comes out of the antenna is 1/10 of what I have here. So in this direction here, so we're looking down at the antenna. In this direction here, I have 1/10 of the output power. -20 dB, what does that mean in terms of a ratio? We said -10 is 1/10, and then another -10 is times 1/10 again, and this is 1/100. So at this point, I have 100 of the signal strength that I have here at the peak. So in this direction here, we have 1/100 of the output power that we see here in this direction. -30, so we add another 1/10. So 1/10 times 1/10 times 1/10, this means 1/1000th at this point. So you see how that signal goes down quite a bit. And we are just dealing with these relatively benign dB numbers. -30 doesn't sound like a lot, but it's 1/1000th of the power level that we have at the peak. And then we keep on going. So in all different directions, we are just painting this graph, and that allows us to say in certain directions we have a strong signal, in other directions we have almost nothing. Does that make sense? Does not make any sense. So the idea is to draw a pattern of where we find the strongest signals as far as our antenna goes. So let's say we have one of these TV antennas that we saw earlier, and it's mounted right here. And when we look at this direction, right off the beam of this antenna, we have the strongest signal. When we look in the other direction, there's almost nothing going this way. So if I point this antenna towards Australia, most of my power will actually go towards Australia, and none of it will go the other way. So I can focus that beam that I'm creating with my antenna on whatever my target is. And the pattern that you see when you buy an antenna, they advertise these, allows you to say, okay, I have a very high front to back ratio here. So there's almost nothing going out the back and a lot going out the front. Yes, there is some going off the sides, which is still quite a bit. And some other antennas actually create a much stronger, and we call this the main lobe, a much more focused main lobe. So it allows you to get an idea about how well your antenna performs in all different horizontal directions.
Would you direct it manually?
Yeah, you either manually, or you can buy an antenna rotor that turns the antenna around.
And you would have like a map or something?
Yeah.
You know, say like a compass directional aiming point?
Yeah.
Okay.
Now, you don't have to do this. I don't have that in my backyard. I just have a piece of wire, and I don't care about where my signal goes, as long as it goes somewhere. But the more money you want to invest, buys you a more dependable way of sending your signal in certain directions.
So wherever you are received is where you talk.
Yes.
Hey, Carl, I got a quick question on that last picture. So the way I'm looking at that is, I feel like I would be in the center of that graph, talking on the radio, and then it looks like the strongest signal is farther away, and because it's at 0 dB, like full power.
Yes.
And the closer that I am, it looks like it is less strength of power. Is that just saying that it takes less power to get closer to where
this has nothing to do with actual distances. The further out this graph is, the more power you have in that direction. So a lot of power in this direction, almost as much power in this direction, and then it gets a little bit weaker. Okay, now we see a decrease, and when we go here, almost no power out the back.
Okay, I gotcha. That cleared it up.
So you've heard me talk about some of these things here. A null means the direction of minimum gain. So our null would be here in this direction. This is an area of minimum gain. The lobes are the regions between the nulls. Now, in this case, we only have one null, so we only have one lobe. The main lobe is the lobe with the highest gain. Again, we only have one lobe, so this is also our main lobe, but it could be a different pattern, and I'll show you some in a few minutes that look different. Side lobes are any lobes other than the main lobes between those nulls. And the forward gain is the gain in the direction assigned as forward. Now, in this case, it's pretty obvious. We would say this is the forward direction. But this may not always be as clear cut. If I have two lobes going out this way, which one do I define as the main lobe if both of them are equally strong? I just have to pick one and say, this is the main lobe. So these are just more terms that we use. So what we've looked at here is the azimuth pattern, the radiation pattern showing gain in all horizontal directions around the antenna. So we're looking down the antenna and we see how the radio waves are spread out in the different directions. We also have an elevation pattern, and that is the radiation pattern showing gain in all vertical angles from the antenna. Now, usually we don't have to look at sending our signal down into the earth, because if we want to fry worms, yeah, okay, we can, but it's not doing much for our signal getting anywhere, so we can ignore that unless we are into spelunking and cave exploration. But usually we care about our signals going above the horizon. So here we have our same azimuth pattern that we had before. Here is a corresponding elevation pattern. And we see our horizon here. And then this is into the earth. We are ignoring that. This is straight up. And here we see we have one main lobe. And this is one of these cases where we have two lobes that are equally well defined. So they actually mirror images of each other. And we just have to say this is the main lobe. We consider this to be the main lobe. And then we have a side lobe here. We have a null here. We have another null here and another side lobe here. So some of our signal is going straight up, but quite a bit is going at this angle here. And if you imagine there's the ionosphere up here, so this might just be the perfect angle to bounce your signal off the ionosphere. Seeing these two patterns, you have to do some mental work to figure out how you actually combine these to figure out what the actual pattern in space looks like. There's software out there that makes it a little bit easier. So these are simulations of an antenna, of my antenna in my backyard, actually, on different bands. And as you see here, a lot of the more red the signal, the surface is, the more signal is going this direction. So most of this signal is actually going straight up here, and we call this a cloud warmer because we're sending the signal straight up. And this is good for some semi-local communication because the signal goes up and comes down again, and I cover a few hundred miles around me. This is on a different band, and we see one strong lobe here, another strong lobe here, and I have to define one of these as the main lobes. And you see like a ton of these little side lobes going in all different directions. So having something like this makes it much easier to visualize what your antenna actually will do than if you have to try to combine in your head the azimuth pattern with the elevation pattern and then trying to figure out how does this look when I actually look at space and not just these two planes. So we've already talked about front to back ratio. There's the ratio of forward gain to gain in the opposite direction. And front to side ratio is the ratio of forward gain to gain at right angles to the forward direction. And all these things describe how well your antenna performs in certain situations. Now, depending on what you want to do, you might not care about this because you say, I just want to talk to people regardless of where they are. You put a piece of wire in your backyard and it will work for you. But if you want to make sure that you talk to the guy in Australia on a regular basis, you very likely want something that has a much more pronounced main lobe so that all the energy goes out in one direction and nothing is wasted. I don't expect you to be antenna designers. This is just to give you some ideas about how antenna performance can be described, but also because some of these terms are actually on the test. Any questions about these antenna basics. John?
When you were doing the null, the lobes, the main lobes, what was the definition of forward gain again?
So forward gain is the gain in the forward direction, and you
Got it.
pick what that forward direction is. Sometimes it's obvious. Like in this case, you say this is the forward direction. But in this case, you don't know which one to pick. So you have to say, okay, this is it. And then the other direction is the back direction. And then you go from there. So oftentimes it's obvious, sometimes not as much.
Yeah, I just wanted to write it down there in my notes. Thank you.
Okay, we said our antenna system also contains feed lines. The purpose of the feed line is to get your RF power from your radio to the antenna. And in ham radio, we deal with two basic types of feed lines. One is coax cable, and you know that from cable TV. It's the same style of coax, but we also have something called open wire line. Sometimes also called ladder line or window line. Why? We'll see when we look at a picture. Regardless of the type of feed line, there's always some power that gets lost. And that power gets lost as heat in the feed line. And we call that feed line loss, and it increases with frequency. Answer to a question on the test. When we talk about coax, we have a center conductor, which is the conductor in the center, as the name implies. We have something called that's dielectric, and that is the insulation surrounding the center conductor. So when you cut open coax, this part here is the dielectric. Sometimes it's foam, sometimes it's solid plastic. The shield is the braid or the foil that is surrounding the dielectric. This part here. And then we have the jacket, which is the protective outer plastic coating. And that is to prevent, mostly to prevent water from getting into the coax, because you do not want water mixing with your coax. That's always bad news. We talk about forward power, and that is the RF power that is traveling towards a load, such as your antenna. So it's power that is going from the radio to the antenna. Now, unfortunately, we also have reflected power, and that is power that's traveling away from the antenna. So it's power that's traveling from the antenna to the radio. Why that happens, more about that in a few minutes. So again, this is our coax, and this is the most common feed line in ham radio. Why? Because it's easy to use. And part of that is it's not affected by nearby materials. So you can run that by big pieces of metal without any problems. Problem with it is it has higher loss than open wire line at most frequencies. There's some exceptions to that, but as a general idea, it has higher loss than open wire line. There is something called air insulated hardline that has the lowest loss, but it's no longer easy to use because you need to keep some protective gas in there in this hardline to keep moisture out, because as I said, water and coax does not mix well. But air insulated hardline is actually the answer to one of the questions. This is open wire line, and when you look down here, you see why it's sometimes called window line, because there are actually windows cut into that plastic between the two conductors. This is lighter and less expensive than coax. It has lower loss than coax at most frequencies. So given all that, why is this not something that we use on a regular basis? It is more difficult to use because it is affected by nearby materials. So you have to keep that about a foot away from anything else. And that makes handling this and running open wire line into your house a lot more complicated. It also requires impedance matching equipment to use with most transceivers. What does this mean? So we talked about impedance. Our radios like to see an impedance of 50 ohms connected to their antenna connectors. And that means we need a feed line that has an impedance of 50 ohms. And we see this with coax cable. The one that we use for ham radio purposes has 50 ohms. Now, if you happen to have a whole roll of cable TV coax in your basement, that actually uses a characteristic impedance of 75 ohms and not your first choice for coax or ham radio. You can use it. There is some loss involved, but if you have the choice, go with 50 ohm coax. Here we have 300 ohms, 450 ohms. So our radios will not be happy when you connect a 300 ohm or a 450 ohm impedance feed line to the antenna connector. This is why you need some matching equipment to match your radio to that feed line. Again, makes it harder to use. So two types, coax, easy to use, open wire line, cheaper, lower loss, but a lot harder to use. So what is this characteristic impedance that I just talked about? That's the impedance that's presented to a wave traveling through a feed line. And it's given in ohms and symbolized in this Z naught. This is not a resistance. So when you put your ohm meter on the feed line, you cannot measure 50 ohms or 75 ohms. This is only an impedance that a traveling wave sees. So don't try to measure it with an ohm meter. You need a lot more complex equipment to determine the characteristic impedance of a feed line. What it is depends on how the feed line is constructed and what materials are used. Coax for ham radio 50 ohms, cable TV 75 ohms. Open wire line comes in different configurations. Our radios expect an impedance of 50 ohms at the antenna connector. This is really important because otherwise our radios will not be happy. And why is that? Because of standing waves. So I have this animation here, and when you look, you see a blue wave traveling this way and a red wave traveling this way. And when you add the amplitude of the blue wave and the red wave at any given point in time, you end up with this black curve. And you see that it's actually standing still. It just changes in amplitude. It goes up and down, but it does not move, unlike the forward power and the reflected power. So we end up, when we have power going both ways, we end up with a standing wave. And that is an important concept. So if the antenna feed point and feed line impedances are not the same, some RF power is getting reflected back towards the transmitter. And this is a bad thing. We try to avoid that. We call that a mismatch. So again, when you add these two waves up, you end up with the standing waves of voltage and current in your feed line. And we can calculate based on how big that wave is the standing wave ratio, or SWR. And we measure this with an SWR meter or an SWR bridge. And in modern radios, this is actually built in so that you know what SWR you have between the radio and the connected feed line. So the radio will actually tell you that it's not happy and will reduce the power when this SWR gets too big. Now, to make matters more complicated, that reflected power is re-reflected at the transmitter and bounces back and forth. But the problem is every time it goes back and forth and back and forth, some of that RF power is lost as heat. And eventually, all the power that we put into that feed line either gets transmitted out the antenna or is lost as heat. And of course, we want to minimize the amount that gets lost as heat. We want to maximize the amount of power that goes out the antenna. So because of that, we need to monitor our SWR, our standing wave ratio. A higher SWR means more reflections and therefore more loss of power. So we want to keep that low. Sometimes you see this referred to as VSWR, or voltage standing wave ratio. For discussing SWR, it doesn't matter whether you call it VSWR or SWR, it's the same thing. So how do we express SWR? We do this as a something to something. If we have a perfect match, we have an SWR of 1 to 1. No power gets reflected, everything goes out the antenna. Up to an SWR of 2 to 1, you can consider your SWR normal, not something that you need to do anything about. Once it goes above 2 to 1, modern radios may lower the transmitter output to protect its power transistors when you go above a 2 to 1 SWR. Once you go above 3 to 1, you have a problem. So 3 to 1, in most cases, you have to do something about it. Sometimes you get erratic SWR readings, and that may indicate a faulty feed line or bad connectors, or something wrong with your antennas, like a piece of wire that is flopping in the wind and getting blown into a tree or against the house at times. So if you see erratic SWR readings, turn the transmitter off and hunt for the problem. If you have a high SWR situation, it can be corrected by tuning or adjusting the antenna. So you bring out your wire clippers and cut some wire off the antenna, or your soldering iron, and you make the antenna longer. There is also called impedance matching equipment, or antenna tuners. You can put them between the transmitter and the feed line, and they are just there to make the radio happy. It does not change anything on the SWR on the feed line. It just means that the radio sees the 50 ohms that it wants to see, the 50 ohm impedance. But what's going on the feed line might still be a problem. So the radio is no longer reducing its power, but you might still have a problem. To measure the SWR meter is inserted in the feed line and indicates the mismatch at that point. So here we have it between the transmitter and the antenna tuner. So in this case, we're measuring the SWR that the radio sees at its antenna connector. If we put the SWR meter here, we would not measure anything that affects the radio directly. We would just measure the SWR between the tuner and the antenna, or the feed line and the antenna. So this is the right way to use the SWR meter, because we want to make our radios happy. Sometimes you use a dummy load. A dummy load is a resistor and a heatsink, and it is used to replace the antenna or other pieces of equipment during testing. You can transmit into a dummy load without actually radiating a signal. So it dissipates all the signal as heat. And this allows you to test your transmitter without actually sending out a signal over the air. And that is helpful in troubleshooting a transmitter or your antenna system. There is a question about the time load on the test. So we're getting close to 8 o'clock, which means you have to do most of these questions on your own, and most of them are pretty straightforward. Let me just show you the 3 questions about the dBs. Which decibel value most closely represents a power increase? This is important. From 5 watts to 10 watts. What's the ratio here?
3 dB.
It's 3 dB, because this is times 2. So 3 dB is the right answer. See, you already know this. Which decibel value most closely represents a power decrease from 12 watts to 3 watts? So if we take 12 watts and cut it in half, what do we get? We get 6 watts. If we take 6 watts and cut it in half, what do we get?
3 watts.
So
almost. So we said this is minus 3 dB. And this is minus 3 dB. And when we combine this, we just say minus 3 dB, minus 3 dB, that is minus 6 dBs.
Oh, okay.
Yep.
So minus 6 dB is the correct answer. But again, there are only 3 questions on the test, so you will know these answers eventually. Which decibel value represents a power increase from 20 watts to 200 watts?
A.
Yep, because this is times 10, so we are dealing with 10 dBs, a 10 dB gain. And these are the 3 questions about the dBs. Okay, here is another question that I wanted to go over. What is the approximate length in inches of a quarter wavelength vertical antenna for 146 megahertz? Whoa. What do they want here?
There was
So,
in the book.
Yes, let me tell you how I do this. The good news is we don't have any kids here, so we don't screw up their math. Let me tell you what I do. So 146 megahertz, what's the wavelength of that? No clue, but 146, that is about 150. And with 150 megahertz, it gets easy. How do we calculate the wavelength? We say lambda is 300 divided by the frequency in megahertz. So 300 divided by 150, that's 2 meters. So my wavelength is 2 meters. It's asking me for a quarter wavelength vertical. So I can either do a quarter here and then convert to feet and inches, or I can say, let's just ignore this for now. 2 meters is about 6 feet. They're about a little more than 3 feet in a meter. Now let's apply the quarters. We take the 6 feet and divide it by 4, and that gives me 1.5 feet. 1.5 feet, that is 12 inches plus 6 inches, that gives me about 18 inches. So my not very accurate math gives me a value of 18 inches. Now I look at the answers here. Is there anything close to 18 inches? Yep. This one is 19. I'm pretty sure this is the right answer. Because my very rough math, just converting the frequency to wavelength, taking a quarter and then converting from meters to feet and inches, gets me really close to this.
Where'd you get the three? Is that 300 just a number that you use to figure out this?
So when we talked about waves 2 weeks ago, there was a formula that we said lambda, the wavelength, is 300 divided by the frequency in megahertz.
Oh, okay.
So if you look 2 weeks back, you should see this formula. And what this actually is a simplified version of taking the speed of light, dividing by the frequency. So we take a shortcut here and say, nobody wants to deal with 300,000 kilometers per second, or actually 299,000 something. We just make a rough approximation and say it's 300 divided by the frequency in megahertz, gives you the wavelength in meters. So that's what I did here. I calculated the approximate wavelength of my frequency and then converted that to feet, and then divided by 4 because we need a quarter wavelength, and that gave me something really close to one of the answers, and that is the correct answer. So 19 inches is the correct answer for this question. And then we have another one. What is the approximate length in inches of a half-wave 6-meter dipole antenna? 6 meters is my wavelength, so I don't even have to do the 300 divided by. It wants half a wavelength, so we divide it by 2, that's 3 meters. 3 meters is about 9 feet. 9 feet in inches is about, I would say 112, because I know that's the right answer. So you can do some really rough math as long as you take the information that you have in the question. So the 6 meter is the wavelength. We want the half wavelength, which means converting by 2 and then converting to feet and inches gives me an approximate number close to the right answer, and then you just pick the one that's closest. Or you do these questions often enough, then you know 112 inches is the right answer for this question. Okay, here is, we're actually at 8 o'clock. Here is a question: what antenna polarization is normally used for long distance CW SSB contacts on the VHF and UHF bands? We have all the guys driving around in their cars with their vertical antennas on their cars, talking via the repeater. So there's a lot of signals going back and forth between the cars and the repeaters and the handhelds that are vertically polarized, because the car antennas go straight up, so they're vertically polarized. The repeater antenna is vertically polarized. So when we talk about ZW and SSB, we are talking about what's called weak signal modes. So when we are on the same bands as all the repeater traffic is happening, how would we avoid interference with all those signals? We can do that by deliberately cross-polarizing our signal so that we reduce the amount of signals that are actually interfering with us. So everybody else is using vertical, which means for these weak signal modes, use horizontally polarized signals. And as we've learned when we talked about cross-polarization, this cuts down the amount of interference that we might be getting by a factor of 100 or more. So that is why you would use horizontal polarization for these weak signal modes. Which of the following causes failure of coax cables? What did I tell you? What does not mix well with coax?
Water.
Water.
Yeah, water.
Yeah. Anytime you see water or moisture and coax in the same sentence, that's bad news. Why should the outer jacket of coax cable be resistant to UV light? Do you see an answer that has water in it?
Heat.
Yeah, UV light can damage the jacket and allow water to enter the cable. We know water in coax is bad news. I think we have 3 questions that all make this point. So if you remember that rule, and then further throughout your ham radio career actually live by it and keep water away from coax, you will pass the test and you will have happy coax. This is a tricky question. Which of the following RF connector types is most suitable for frequencies above 400 megahertz? So in which segment is 400 megahertz?
VHF, right? Isn't it?
It's UHF. It's actually 300 megahertz to 3 gigahertz.
Yeah, UHF is the highest, right? That's what it is.
Yeah. So 400 megahertz is in the UHF segment. We will not use the UHF connector for this. Why? Because this UHF stands for something completely different than this, and it's just a coincidence. It's a really bad choice of names, but this UHF actually goes back a long time. So the right answer for this is actually the type N connector. So do not let the question mislead you. We do not want to use a UHF connector for UHF signals. We want to use a type N connector. UHF, this particular connector is not suitable for higher frequencies. It works fine for HF and lower VHF, but if you go up higher, your UHF connector will fail. So use a type N connector. Okay, so we went through those questions that I thought required some discussion. The rest you should be able to do on your own. We went again a little bit over, but we made it. Any questions from you regarding propagation, antennas, feed lines, SWR?
No.
I know it was, again, a lot of information. But I think this is a little bit easier to understand than what we did last week. Impedances, reactances, and all that kind of stuff. that just goes straight over my head. Antennas, okay, there's something to actually try to understand there. I hope you feel the same way. And if not yet, just practice those questions. You will get through them, and you will get to the point where you say, yep, I know, 10 dB, that's the answer. So if you don't have anything for me for next week, look at chapter 5. That should be a little bit easier than what we've done so far. And keep on practicing the questions of the previous weeks. So don't forget about week 2 and week 3 as we move forward. By next week, after week 5, we will be at the halfway point. And then it makes sense to start doing these full 35 question sample tests. And you know that you've only covered 50% of the stuff. So you will not get every single answer correct. But by doing them, you get into the groove, and you will see that some of the questions that you have not seen yet, you will actually be able to answer just with a little bit of common sense. And you will also get a better idea about where you are in your progress towards taking the test. And if you end up getting 9 out of 10 of these sample tests correct way before the end of class, don't wait. Go sign up for the next test and take the test because you are ready. If you don't quite do as well, don't worry, you will get there. So far, everybody who wanted to pass the test passed the test. It may not work the first time you try it, but we will get you there. With that said, have a great week, and I hope to see you again next Tuesday.
Thank you, Carl.
Thank you very much, Carl.
Yeah,
Bye.
thanks, Carl.